All right, it says here, use the formula for the area of a circle in arguments involving proportions to derive the area of a sector formula. This one's called a formal example. I think that's the first of those that we've seen. So I sometimes do formal examples that are kind of like a derivation or like a proof of a theorem it would be in a math class. But in physics classes, we do derivations more often than not. But they do get a little more formal in the math. It's kind of like I'm presenting either a proof or kind of a pseudo proof of some result. It would be way too much time to do that for everything in this class, so I usually pick and choose ones where I think it's kind of nice, and I think I'm doing this one just to highlight how you could understand the area of a sector formula in a new and neat sort of way. Sometimes I will just show the answer, because usually with formal examples I have more of the steps worked out when I show the answer in the slide. Sometimes I will write more of it on the board over here. I think I'm going to write a little bit on over here, and then we'll check the answer when I maybe get tired of doing that. But it says use the formula for the area of a circle. So let me see. Area of a circle, I think, is pi r squared. Hopefully I didn't have to Google that, but it's okay if you feel tired, I guess. So pi r squared. And then it says arguments involving proportions. Well, pi r squared, right? But this is for, if I think about, like, I'm thinking about like a whole circle, and I've said in examples we often like to draw pictures, right? Our goal is to find the area of a sector, which maybe I could think of that and say, hey, this is like the sector of a circle. A sector of a circle is defined by some angle theta. In that sense, if the area of that slice is, if I think of that as like being a function of theta, I'm basically being asked, tell me what that function is, right? And I'm using function notation here, even though I don't emphasize functions a lot, but it's kind of convenient to talk about this in that way. But okay, a couple things I think that is true is, one is, if I were to relate this to what I already stated about a full circle, isn't that just the same as saying that this area as a function of angle, if it's the whole circle, the angle for a full circle, isn't that just equal to 2 pi? In that sense, like if I said, hey, here's a sector, now let's just keep growing it by increasing the angle. What happens when theta equals 2 pi? Well, you've got a whole circle, right? So in other words, I've already got one value for this function. When theta is equal to 2 pi, the area had better be equal to pi r squared. Now, it said to use some arguments involving proportions. By the way, I struggle with r sometimes on boards. You might notice that. But anyway, it says like to use proportions. I think a simple observation I can make is I think this area of a sector should be proportional to the size of the angle. If you double the angle, you've got double the sized sector, therefore double the area. I also know that area should be proportional to radius squared, because that needs to be true for the units, right? It needs to be a length squared, and an angle is not actually a length, right? That was a dimensionless unit we saw the radian was, right? So between these two and maybe this information, I can figure it out, right? Because this suggests that this area as a function of theta should be equal to, this kind of like that time machine problem I think we did earlier. There should be some k times a theta times an r squared that would answer this. But if I look at this one right here, right, when theta is equal to 2 pi, it turned out to be pi r squared. I think that means k has to be equal to 1/2, because then, right, because in that case I would get like a, I don't know how to write this. Hopefully this makes sense to everybody, but I'm kind of guessing. I'm ready to make an educated guess that maybe k is 1/2, so I'm making that replacement. I'm replacing theta by 2 pi, and I'm just checking if this works with what I already know. Then I'd get 1/2 times 2 pi r squared, and that is in fact what I already know to be pi r squared. So what that suggests to me is my guess that k was equal to 1/2 had to be correct, and so therefore the formula for the area of a sector must be equal to 1/2 theta r squared. So anyways, that's kind of my somewhat messy derivation. I don't know if it's really a proof because I did some guesswork on the way there that might not cut mustard in a math class. Here is the version on the slide, and it notes the same two proportions. It says, therefore, there must be a k theta r squared. It points out that for theta equals 2 pi, the area of the sector must be pi r squared, and therefore k must be equal to 1/2. There's probably, you know, I didn't show the steps in the slide, but I just guessed that when I did it here. There probably would have been a more algebraic way of getting there. I just didn't really feel like I had the space to show it, so I just made a guess. But that wound up leading to this result. So you can kind of see how that result, another way of putting it is, it makes sense. Given this information I understand about this, that's the only thing that makes sense. And I have found that useful to help me remember stuff that may be less valuable these days, where you can look up information really, really easily. But sometimes it's still cool to kind of, you know, to know things like that, I think.